Okay. Hopefully everybody's first week is going well, right? Hopefully it's going pretty smooth. Welcome to Lecture 3. I know that it was the difficulty of the last homework probably bordered on a violation of the Eighth Amendment. But the idea was just to shake off the rust, so hopefully it wasn't that bad. Okay, I've got the attendance grades posted. They are up to date. The way that the class will work is the solution will be posted on Monday. Not that it probably matters now, but typically what we'll do, for example, if I assign a homework Monday that's due Wednesday, the solution will be available on Friday. And so that pattern will just keep going. And so from here on out, like every semester or every homework, that'll happen. So you're going to have a homework that is assigned today that is due Monday at 11. I am curious if you have the same technological hiccups, because I had set this homework up the same as the last one, as well as a homework in another class, but for some reason this assignment, like as soon as it opened, a lot of people couldn't access it. If that happens again, let me know, and I'll manually do it. I have them set to turn on, but for some reason that was causing some glitches. I did want to also mention that I have lecture notes now posted through Exam 1, so I just wanted to kind of show you what that's like. I'll pull the QR code up again here in a second. But if you go to the class, okay, we'll go to student preview so you all can see what it looks like. So this just made live now. So a couple things worth mentioning. So if you go to course content, you'll now see a folder called older homework assignments. What I'm going to try and do is if there's a homework that's graded, what I'll do is I'll put the homework in there, because if I don't, you're going to log in and just see tons of assignments. So once they're graded, I'll try and stick them in there so it'll reduce the clutter on the page. But on Monday, there will be yet another folder here that says solutions to older homework assignments. And when you click that, you'll see the assignment and the solution all in one spot. So that way they'll all kind of be there. If you go to lecture notes and supplements, though, you'll now see a few more things. So you'll see course overview, topic 1, which we did last time, we're doing today. Topic 2, which is the statics of particles. That's going to be sort of our big topic on the exam. And you can see, like every day there's a PowerPoint, and that'll go all the way through the first exam. So that's lectures 4 through 10. When you go to Exam 1 review, you'll see also an exam review PowerPoint slide. We'll bring this up during the exam review day. But like, for example, if you look at that, you'll see like some info on the exam, and then you'll see like all the necessary formulas sort of all in one spot. Right now, it probably seems like information overload, but by the time we get to that point, all that stuff will be pretty digestible. Does that sound good? Okay, so like I said, I try and keep the Blackboard shell tidy, so I will do my best throughout the semester on that. Okay, all right. Did everybody get the code? The QR code? I'll give you a second. Everybody good? Okay, all right, so Lecture 3. Okay, so if you recall last time, we were discussing this dimensional analysis example. I kind of knew we weren't going to have time to do it, so I want to do this today. We're just going to jump right into it. So if you recall, in addition to being able to do unit conversions, one of the things that I just think should be a valuable skill among all engineering students is to be able to determine whether or not an expression is dimensionally consistent. Okay, so I've proposed to assess that using Bernoulli's equation. Bernoulli's equation is a means of calculating the total amount of energy in a fluid conduit. So if we have a pipe that's carrying, liquid mercury, for example, it is a function of the pressure of the fluid, the velocity of the fluid, and the fluid's elevation. So in order to determine the total amount of energy, we need a number of terms. We need the fluid's pressure, which is always going to be a force per length squared, like pounds per square inch or newtons per square meter, which, by the way, very rarely will you, in the future, will you see pressure in SI referred to in newtons per square meter. It'll probably be referred to in pascals, because a pascal is a newton per square meter. There's a reason I'm referring to it like this in here, and that'll probably become pretty apparent here in a second. You also need the fluid's unit weight. So this is, if I had a cubic meter of the fluid, how much would that cubic meter weigh? And that is a property of the fluid, like mercury or gasoline or water or whatever. They all have different unit weights. We need the fluid's velocity. We need the fluid's acceleration we need acceleration due to gravity, not the fluids, just acceleration due to gravity on Earth. And we also need the fluid's elevation with respect to a common datum. And so what we're going to do is we're going to add these terms. This is what Bernoulli's equation tells us to do, but I want to see if this is dimensionally consistent, okay? And so I'll show you what I mean by that. If you notice, what we're doing is we're adding 3 terms, okay? Now we're adding 3 terms. What you can't do in physics, you cannot say I'm going to have 7 meters and then say I have 7 meters and let's add 3 hours. That doesn't make sense, right? We need to add 7 meters to 4 meters, to 7 meters, to 12 meters, right? If you're adding terms that are being added must be dimensionally consistent. So we're adding these 3 terms. Let's see if the units work out, okay? So let's see what we've got here. So we have the total energy equals the following, okay? And so the way that we're going to do this is we're going to say, okay, we're going to write this equation over again, pressure over this. This is the Greek letter gamma, by the way. If it looks like this weird looking Y, that's the lowercase gamma. You might have seen that before, but if not, it's engineering. We use a lot of Greek letters, so you'll get used to that. Okay, so P over gamma, V squared over 2GH. I'm going to start replacing that with the unit equivalents. A lot of times when I do a dimensional analysis, I'll write the units in brackets just to sort of indicate that I'm not actually doing calculations. I'm just checking the dimensions. So I'll sort of write it as, so I have a fraction here, so we'll write this as newtons per meter squared divided by newtons per meter cubed, okay? And just to sort of follow along so you all can see what I'm doing, this is P over gamma, right? So P is the pressure, right? So P is the pressure, and pressure is written in Newton per square meter, so I'm writing Newton per square meter and then Newton per cubic meter because that's what gamma is written in. And like I said, I'm writing it in brackets because I'm not doing a calculation. And this next term, you'll definitely see why I'm doing that, okay? So what I'm going to do, so we'll say this right here, let's write it right here. This is P over gamma, okay? Then I'm going to add to that the next term, okay? And the next term is V squared over 2G, okay? So I'm going to say, okay, here's a fraction. On top, I have V squared, okay? So V squared, I've got this term squared. And what I'm squaring is the velocity, which is expressed in meters per second. So we'll write it like this, meters per second, okay? Now on the bottom, we have gravity. Gravity is going to be meters per second squared. And I'm going to say that this term right here, that this equation, or this expression, I should say, is V squared over 2G. But notice how I forgot something. What did I forget? The 2, right? I am purposefully not incorporating that because when I'm doing a dimensional analysis, the constants don't matter. And here's why. If I have, I don't know, 24 meters, and I take 24 meters and I multiply it by 2, I get 48 meters, right? A constant multiple does not affect the unit system, right? I'm not performing calculations. I'm performing a dimensional analysis. I'm referencing that by writing these terms in brackets, but as a result, I'm also not throwing in the constant terms, okay? Because the constants won't affect the units. Does that make sense? That's sort of like my way of expressing that, okay? And then my last term over here is the height, the elevation, and that's just in meters, okay? So this is my H term. So you can see what I'm doing is I'm just sort of representing the unit systems for these in one fell swoop, okay? So let's see what would happen if we start to expand this out, okay? So what I'm going to do in this next line is I'm going to rewrite things a little bit. I have a fraction divided by a fraction. So how do I divide fractions? Do y'all remember how to do that? If I have a fraction divided by a fraction.
Multiply by the reciprocal.
Flip and multiply by the reciprocal. So what I'm going to say is this is Newton per square meter multiplied by cubic meter per Newton. You see what I'm doing there? So this fraction goes here, and then I reciprocate, multiply. Okay? And I'm going to do the same thing over here, but I'm going to be a little crafty over here, so let's deal with this numerator first. Okay. So if I have the quantity meters per second squared, that's just going to be meters squared over second squared, right? I just square each individual term. So I'm going to have meters squared over second squared times, and then I flip that bottom fraction and multiply, so second squared over meters. Plus, and then I've got that. I'm breaking out all the colors on this calculation, but you can see what I'm doing is it's just got a term plus a term plus a term, okay? Then let's see what happens with our unit systems, right? So let's take the first one, right? What's going to happen to the newtons?
Cancel out.
They cancel, and I have meters cubed over meters squared, which is meters, right? So we can say that cancels, and I'm going to be left with meters. What about over here? I've got second squared, they cancel, and I'm going to be left with meters, right? And then meters here. So is this expression dimensionally consistent? Yes, it is. So one thought experiment would be, what if the problem had been P over gamma plus V squared over 2G plus H squared? Would that have been dimensionally consistent? No. Or what if it had been, I don't know, V squared over 2G plus V? You know, that wouldn't have been dimensionally consistent, right? So the idea, that's the idea, is to investigate dimensional consistency. So on your homework, I'm giving you sort of a formula, and I'll pull the homework up here in a bit. But I'm giving you another expression where I have a term equal to a term, and I want you to investigate to see whether or not it makes sense. Are you getting this unit system equals this unit system? So it's pretty straightforward, but it's kind of the same idea. Does that make sense? All right. So far, so good? All right, okay. All right. Any questions before we move on? Okay. Now, this is a class that is going to require some basic computations and some basic understanding of physics and math. What bugged me, I know, when I was a student, is there's a problem in class that's like super easy, and then you get to the homework assignment and it's ridiculous, right? Or you get to the exam and it's crazy, right? So what I don't want is a situation like this where I'm the professor who says the problems in class are really easy, and I don't want that. I don't want to do that. But in order for that to be the case, everything needs to be comparable, but you also need sort of an understanding of what knowledge you need coming into the class, okay? And so last time, our star of the show was physics, okay? What physics concepts do you need in order to be able to negotiate Engineering 213? Today I want to talk about math. What math concepts do you need in order to be able to negotiate the class? Now, we're going to talk about 3 disciplines. We're going to talk about algebra, calculus, but the real star of the show and what really is the big, mathematical demand in Engineering 213 and Engineering Mechanics is trig, okay? So we're going to be using a fair amount of trig in here, okay? So I want to just make sure we're all on the same page on the types of calculations that we're going to do in here. And I think that this presentation's pretty exhaustive on everything that you'll need in order to be able to do this class, okay? So let's start off with algebra, okay? So number 1, you do need to be able to do some basic operations in algebra, factoring or distributing. So, like stuff like this, if I have A times a quantity B plus C, that means AB plus AC. Like, just make sure you understand stuff like that. Understanding how to negotiate the quadratic formula is a pretty good idea. If you understand how to graph a function, that's a big plus in here. Probably what is going to be our most utilized algebraic skill, or at least one that you haven't probably done in a while, is this, okay? Do y'all remember these problems in algebra where you're given 2 simultaneous equations and you must determine the magical value of x and y that satisfies both equations? We're going to do these types of problems quite a bit in here. And we're going to do both. This, I would refer to this as a 2x2 system of equations because there's 2 equations and 2 unknowns. We're not only going to be dealing with 2x2 systems, but 3x3 systems. Why? Because we have 2D and 3D, right? So we are going to be doing this quite a bit. Now, I have no problem if you surrender to the Casio FX115 ES Plus or similar scientific calculator in order to be able to do this. In fact, I sort of recommend that you do because this is, what I do not want this class to be is you've done a bunch of statics and then you have to do 15 minutes of math that, this is a statics class, it's not a math class. I have no problem if you utilize your calculator to do a lot of these functions. We're actually going to review that when we get to that point, how to use your Casio, how to do this. In the past, what I had done is I curated a playlist on YouTube that went through how to do simultaneous equation solving for this and a number of other calculators, so that way everybody knows how to do it in yours, okay? So I just mentioned that. But we are going to be doing this pretty soon, probably within the next week and a half or so. Okay, trig, okay? This is a big star of the show, so I do want to spend a little bit of time on this. First off, so why is trig important? Okay, so this course is a course in engineering mechanics, but the most fundamental object that we're going to be using this semester in order to describe situations in engineering mechanics is the vector, okay? And we're going to be doing a lot of vector math, a lot of vector addition, okay? We're going to be doing vector multiplication later and what that even means. Was that yours? Oh, sorry, I thought that's what you were reaching for.
I think so.
No problem. I thought that was yours. So we're going to be doing a lot of vector addition, and vector addition is a graphical process by nature. In other words, so if you have vector A and vector B and you add them, you stick them tip to tail, right? So if you want to know what the sum of vector A and vector B is, it is that remaining leg in the triangle. So we're going to be doing a lot of triangular analyses. So understanding things like this, like the sum of the interior angles in a triangle is 180. I know it's basic, but we're going to be doing this stuff quite a bit, so I just want to make sure we're all on the same page. Things like what is a complementary angle, what is a supplementary angle? A complementary angle is such that 2 angles add up to a right angle, or supplementary angles so that they add up to 180. Y'all remember this from geometry, right? That angles 1, 4, 5, and 8 are all equal, right? If these are 2 parallel lines cut by a transversal, and angles 2, 3, 6, and 7 are all the same. Remember that? We are going to be kind of using that stuff in here. So When I just, like, if I draw a vector problem and I just sort of say, oh, that's 20 degrees, you're like, well, how did he come up with that? Well, it's this, okay? So I will take my time and go through it when we get to those computations, but I want these ideas sort of like, you know, in a little bit of recall in the back of your head so that when we start going to these calculations, oh yeah, that's what he was talking about, okay? So we are going to be doing this. Basic trig functions, SOHCAHTOA. You know, for example, if we have a right triangle, understanding how to compute the sine and cosine and tangent of an angle in that right triangle. And to be clear, what we're doing in here is very fundamental trigonometry. I mean, when you take a course in trigonometry, this is where it starts, but then you go, well, the sine and cosine are ratios in a right triangle, but really what they are is wave functions. Well, no, wait, actually, really what they are is coordinates on a unit circle. We're not going into that world about, you know, math theory as a word. We're using tricks. So, like, this is sort of where it stops. I'm not going to expect you to go, okay, what's the amplitude and frequency of the sine wave? We're not doing that in here, okay? I'm not saying it's not important, it's just not important in here, okay? But being able to compute the various ratios on a right triangle, very important. Sines and cosines, we're going to be doing sines and cosines all semester, so just be ready for that. Pythagorean theorem, that's sort of a must in here, just being able to negotiate that. So far, so good? One thing we are going to need to be able to do is convert between rectangular coordinates and polar coordinates, okay? In other words, what we're going to do is take a vector in 2 dimensions and break it up into its x and y components, okay? That is going to be a very useful skill very soon, okay? And we're going to be doing that pretty much all semester. Being able to do this and this, vice versa, this is pretty relevant. Even going the other way is relevant too, because when we have a bunch of vectors that we've added up, one of the things that we're going to want to do is find the resultant vector at the end of the day. And the resultant vector at the end of the day is going to be defined by its magnitude and direction. And so using this side to do that is going to be very important as well. So that's going to be very important a little bit later. Okay, law of sines and law of cosines. We're actually going to start using that today. Remember that? Like, so law and sine, the law of sines and the law of cosines are when you do not have a right triangle, when you have a scaling triangle or just an arbitrary triangle, being able to solve that. So I would say sort of like the third fact on top of this are things like being able to understand that the sum of the interior angles is 180 degrees. But the law of sines and the law of cosines is meant to solve arbitrary triangles. And in a triangular analysis, you're given 3 data points, you need to solve for the other 3, okay? And so we're going to have problems like that very, very, very soon, okay? Doing well on time. Okay. So far, so good? Okay. All right. Calculus. I know y'all probably hit your limit with all these calculus jokes. Well, no. I know, I'm sorry. So I'll say this. We're actually not really going to do a ton of differentiation in here. I will throw some derivatives on some slides for the purposes of explaining some concepts. What we are going to do are some integrals, okay? We're going to need to be able to integrate in order to define the area of shapes and more specifically the location of the center of gravity of a shape. So once we get into the October-ish time frame, being able to negotiate integrals is important for locating centers of gravity or an idea related to that, which is locating a centroid, okay? And being able to do this is important. Now, when I say being able to do this is important, what I mean is being able to integrate x squared. I do not mean being able to integrate the tangent of e to the square root of x from 0 to pi over 4. We're not doing, you know, those types of integrals in here, okay? It's pretty basic stuff, but we are going to integrate in here, so I just want to mention that. But that won't be until October-ish, November, something like that. So for now, trig is going to be the star of the show in here. So far, so good? Okay. Has it been a while since you've done a problem like that? Been a while, right? We're going to do a problem like that right now because the reason that I'm doing this problem, I am convinced everybody in here can do this, and I'm sure that some of you are probably like, we know how to do this, but it's also probably been a while for a lot of you too. And we're going to start doing this, on Monday, so for vector analysis. So I just want to take a step back and make sure that we're all comfortable with stuff that I know it might not have been a while, or it might have been a while since we've done it, but it is important, okay? So what I'm giving you is what I think is a representative trig problem that if you can do this, it will make our first foray into vectors a lot smoother, okay? So I'm giving you a triangle, an arbitrary triangle, and I've given you 3 data points about this triangle. I've given you 2 of the interior angles and the length of 1 of the sides. And just from observation, I think you can tell that this is not a right triangle because I have 80 and 41, they don't add up to 90. If they don't add up to 90, that third angle isn't 90, right? This is not a right triangle, okay? What I want to do is I want to solve for the other 3 components. What is angle A? What is this side and this side, okay? Now, what I say here in this box is important. Not just for this problem, but for the class in general. For this problem, there are multiple different ways that you could do this problem, and there is no one right way. And more generally, I am not one of those professors that says, you didn't do it my way, so take your homework and burn it. I'm not one of those professors. And I know that you've had those professors before, right? I'm not that. I don't care as long as you do it, as long as you get the right answer. And perform your calculations neatly and in an easily discernible fashion, you have a lot of flexibility to do it the way that you want. I am going to do this problem in a manner that uses sort of like what I would say the 3 most common equations that you would need. So the interior angles, law of sines, and law of cosines, mainly as an educational review of these equations. But you don't, like for example, some of you are going to say, well, why couldn't you use the law of sines twice? You could. That's fine. I have no problem with that. Okay? Everybody good? Now I'm going to begin with what I believe is the easiest term to solve for, and that's this angle, right? I think that's the easiest term to figure out. Okay? So I'm going to begin by... I'm going to have to turn off my touch screen. That is going to get annoying. So we're going to begin by solving for that interior angle A. And how are we going to do that? There you go, exactly. 180 minus the sum of B and C. So 41 and 80 is 121. 121 off of 180 is 959. I get that right? Okay. All right. That shouldn't be so bad. So the next thing that we have to do is we have to solve for our 2 remaining sides. I am going to use we could use the law of sines or the law of cosines, given the information that we have. I'm going to utilize the law of sines first. I think most folks would agree it's the least cumbersome. The law of cosines the equation is a lot longer. There's a lot more button crunching. So I'm going to use the law of sines first. And I'm going to solve for C. Okay. Now remember, the law of sines is always applicable whenever you have a pair of opposing values. In other words, for this triangle, and I'm just going to use given information, I know angle B and its opposing side B. I know that, right? So if I know this and this, I can look at another opposing pair, for example, this, and solve for C, right? Now, there's two different ways of writing this. I could say sine, here, I'll use red. I could say sine of C over C equals sine of B over B. I could write it this way, or I could reciprocate both sides. That would be fine too. In other words, I can say C over sine of C equals B over sine of B. In other words, I think in my presentation or my slides, I wrote it that way, but you can write it that way too. That's fine. I kind of like it this way for this problem because I'm trying to solve for this little side C, so I can just multiply both sides. And I can say, therefore, and by the way, if you ever see me write these three dots in a little triangle like that, that's shorthand for therefore. That's what the term therefore means. So C equals like that, right? So that's going to be 71.4. We'll do it like that. Sine of, what is that, 41 degrees. Sine of 80 degrees. So I need some help from all of you. And by the way, make sure that when you're calculating this out that you're using degree mode and not radian mode in your calculator. I imagine if some of you are currently in a calculus class that your calculator may be in radian mode. So is anybody getting a value for C? We'll say 2 decimal places just for the purposes of what we're doing in class. 107.18. Do I have a second on that?
Yes.
Okay. Not too bad, right? So we've got that. So if we go to our triangle, here, let me scroll up a little bit. I'll have to call them back. All right, so I've got all the interior angles solved. I have this side solved. The only thing I have left is this. Now, I could just use the law of sines again to solve for this angle, and there's nothing preventing me from doing that. I'm going to use the law of cosines mainly as a mental refresher. Sometimes the law of cosines has to be used. For example, if you start a problem and you know this side, and the angle between them, you kind of have to start with the law of cosines in order to solve for the opposing side and go from there. So I want to make sure that we're all familiar with how to do that, okay? And by the way, the handwriting's coming through clear? Everybody can see that? Okay. If you ever need me, like we're going to have problems that just sort of get longer and longer, so if you ever need me to scroll back up, let me know. I try and not scroll up and down too much so that you all can follow, but let me know if I'm doing that too much. Okay. All right. So I'm solving for A, and so fortunately the law of cosines has multiple ways of writing it, so it is kind of easy to figure out which one you need to use. So we'll say that A squared equals, and remember the law of cosines is just the Pythagorean theorem minus some other stuff. Basically, it's what it is, right? So we just take A squared equals B squared plus C squared minus this hullabaloo. That is a very technical term, by the way, hullabaloo. All right. So what I'm going to do is I'm just going to plug in on this side, and that's going to yield an A squared. So don't forget, I got to take the square root of that at the end. Okay, so B is 71.4 squared minus 107.18 squared minus 2 times 71.4, 107.18, and then the cosine of 59 degrees. And so let's just chug this out first before we take the square root. Let's just make sure we're all getting the same answer here. I'm gonna down a little bit. There we go. Anybody have an answer for me just on the a squared? 0.6 what?
698.
So we'll say 8702.70. Do I have a second?
That's what I know.
Okay. So therefore, that's a squared. That's not a. So therefore, a is just the root of that. So that, and then we get an a value of, I got
93.29.
two, okay. 93.29. So typically, just so everybody's aware, what I like to do is we're going to have problems that just get longer and there's just a lot of steps and a lot of stuff. So I usually like to write a little summary at the end and just make sure that we've got the answer in one fell swoop. So we have an a value of 59 degrees. We have a little a value of 93.29, and then a c value of 107.18. Yes, sir.
How did the plus between b squared plus c squared become a subtraction?
It was not supposed to be.
Okay, because I got 62.
That was a boo-boo. It was supposed to be a plus.
Okay.
Yeah. See, Marshall University policy says I'm allowed 7 mistakes per semester, but I'm the one that tracks the mistakes, so it's a corrupt system, I know. No, that's an honest mistake. That's supposed to be a plus. Yeah, if you see if you see an error in a calculation, let me know. I will remember it. By the way, that's a joke. Again, am I that scary? I hope not. I'm just having fun with this. All right. Is this bringing it back? It's been a while since you've done this stuff, right? But we are going to be doing it. I tend to think it's healthy to take a second and go back through this instead of just, nose diving into vectors, because I think when we actually start covering vectors, we're actually able to go through the problems a lot faster because we all got in the right headspace before we started. Okay, so I think that's a pretty healthy exercise. Okay. Any questions? All right, so let me pull up the homework assignment just to show you what it looks like. It'll be another quiz on Blackboard, but just to give you kind of an idea of what it looks like. This will be the last one that is a quiz. Everything else you'll upload scanned PDFs. And just to let everybody in, the reason why is because, bless you, we can't start our TAs until week 2. So week 1, I have it graded itself. Okay. So on problem 1, I'm giving you this equation right here. So it's a term equals another term. And so F is a force, X is a distance, T is time, and so on and so forth. And I want you to say whether or not it's dimensionally consistent. So it'll just say true or false. It's either dimensionally consistent or not. But I do think, go through the exercise of doing it. Okay. For problem 2, I'm giving you a right triangle, and I'm saying just tell me how long C is. Round your answer to 2 decimal places. And then problem 3, I am giving you this triangle, and I'm saying determine the value of A to 2 decimal places. That's due Monday. Not bad, right?
Nope.
Sound good? Any questions? Well, I'm going to pull up the QR code one more time, and I'm going to give you 11 minutes of your life back. And you all have a wonderful weekend. I will see you all on Monday.